Um, Great to be here. Thanks for having me. Thanks to the organizers. This has really been a fun conference. Looking forward to the next few days. For those I haven't met, my name is Sam. I'm a grad student at Columbia University. In my fourth year, I study sea level change and the connection between the cryosphere and the deep Earth. Um, Ice field and JERP has not been the main focus of my PhD, but I've had the opportunity to be up on the ice field in a teaching role, and through that, spun up some research projects that are very much ongoing, and I'm excited to share today and looking for feedback from this community, sort of about research directions and general interest. Um, so I think everyone's very familiar with this. Alaskan glaciers and the Freon ice field are melting rapidly. Alaskan glaciers in particular make up 25% approximately of the glacier mass loss globally as of 2021 at least. The Juneau ice field in particular has been very well studied, as we all know, and thought to be accelerating in its mass loss since the Little Ice Age. And we care about all this because as of recently, ice sheets and glaciers are now the largest contributor to global sea level rise, which affects coastal communities around the world. This is sort of the central theme of the geoscience that I think about. And in particular, I think about anomalies or exceptions to this rule. So sea level is rising globally, but it is falling in Alaska. And this has implications for people off Alaskan coastlines who are very much connected to the ocean, culturally, economically. And so this is something we want to understand in the modern and also be able to project into the future. And it contributes to our overall budget of global sea level. Why is sea level falling? It's primarily related in Alaska to an effect called glacial isostatic adjustment, GIA. I'm not going to get too into the weeds of what GIA is. The sort of technical term is the viscoelastic response to the Earth's solid surface, geoid or gravity field, and rotational axis to changes in ice and ocean load. Ice sheets are heavy and they have a lot of mass. And when they grow, they deform the solid Earth and create a depression under them. As topography falls, sea level rises. Big ice sheets also attract water because of their big gravitational pull. And most importantly for today, when ice sheets melt, the land rebounds, which has the effect of relative sea level falling. You also have less mass attracting water, so you also get sea level fall that way. And in very simple terms, GIA is a function of two things: changing ice load, so where mass is on Earth and how fast it's changing, and the rheology of the solid Earth, so how squishy it is when you melt an ice sheet, how much is it going to respond or deform, and on what timescales and spatial wavelengths. People have studied this across Alaska. This is one of the most recent assessments. On the left, in the colors, is satellite product for ice surface thinning or thickening. And then the arrows are GPS constraint uplift rates, vertical motion. And you can see across most Southeast Alaska, land is rising. And then people have sort of linked these two through GIA modeling. You get this much mass loss constrained with the GPS, and you can create a full field of what uplift is doing. And this creates, this has a significant contribution to the overall sea level budget. It's the primary process affecting sea level. But you'll also see in that big blue circle, that's where the Juneau ice field is, and there's a big data gap. I'll think this satellite product for ice sheet or glacier thinning is great, but we can probably refine that in this area as well. So I'm really interested in Juneau ice field as a case study for GIA, leveraging years worth of research from the mass balance side to the GPS side. So using this as a case study to connect isostatic rebounds to uplift and constrain, hopefully ultimately, the local sea level fall or the contribution to sea level fall. And we're currently doing this with two ongoing projects. The first is measuring that rate of isostatic rebound, trying to fill that data gap in ice field. And then the second, generating a high resolution ice loading history using some ice elevation data that JERP's collected over the past few decades. So these are sort of the two ongoing projects I'll talk about today. So starting with measuring modern uplift rates on the Juneau ice field. This is in collaboration with everyone at JERP, but in particular, this set of students who took on this project during the Block 3 student-led research section. And I really want to highlight JERP undergrad program here. Sort of everything I motivated at the beginning was just an idea I had coming to the ice field. And over the course of one summer, that idea morphed into this project that was designed and implemented by students, which was really, really cool to see. This would never have happened without the undergrad program, without like the motivation of a bunch of really engaged young scientists. And it lives on. Miranda Dawson is a student at Barnard, is going to continue thinking about this for her senior thesis. I think it's really cool that someone gets to work with data they collected in the field for the thesis. That's like not an opportunity I had as an undergrad. I think it's really great. And these are just some images of students planning overnight trips and working out some science communication talks related to GIA. Just another highlighting JERP as a testing ground for new systems. I went up there with this new GPS unit that our group had bought a couple of years ago and never bothered to use because they didn't want to take it to the field and have it break. So JERP offered a great opportunity for me to test this device, make sure it works. It was the AeroGold Plus differential GPS with Atlas real-time correction. It's really nice. We didn't have to use a base station. We could just roam around with one unit, had a battery that lasted all day. Required about 45 minutes to lock or reduce uncertainty to like sub 10 centimeter uncertainty. Once you had that, you could move around, keep it upright. And I think it simplified the whole process quite a bit. We did have a little battery issue, which was just me forgetting the charger back in Juneau. And so not really a battery issue or a me issue, but Scott lent us a charger, but then Scott left with the charger, and I thought our season was over. And I was very disappointed in myself. But JERP stepped in again. Greg Carpaccio, one of the field staff, spliced up a student laptop charger and soldered a USB-C cable to it, and it saved the GPS and it saved this season. None of this, I wouldn't be talking about any of this if that hadn't happened. So another great thing that JERP offers is the field support. Okay, what do we actually do? So we're building on an existing JERP GPS survey that's been led by Scott McGee and the USGS for a long time on the ice field. They installed 20 plus survey markers on Unitax. These markers are used to put base stations out to then conduct the on-ice surveys, but in a couple locations, they measured the absolute elevation of these markers in 1995. And so we're able to go and repeat those measurements and see how much the land has changed since the 90s. And then while we were at it, we also measured the absolute elevation of 16 other survey markers, which just provides a nice baseline for potential future work. Maybe 5-6 years, we can come back and remeasure those. So this is kind of a silly plot, just has 2 data points, but I think it's really cool. It's what we got out of the summer. We measured uplift of 2.3 and 2.7 centimeters per year at Camp 10, Camp 18. These are much higher rates than were predicted by previous studies for this area. Of course, they had no data to constrain it, but this is a lot higher, I think, than we thought initially. We can compare to some time series for permanent GPS installations in Juneau and another site to the west of the ice field. They give 2.1, 2.6 centimeters per year linear uplift rates. And I'll note that the uplift rates we derived are averaged over the past 30 years. And assuming that the ice field is accelerating in its rate of melt, we might imagine that for the past few years, that rate is actually a lot higher. There's some exponential component to this. Here's what this looks like in sort of map view. Here are the 2 points that we measured on the ice field, Camp 18 and Camp 10, in context of other data that's available. We sort of see that there's greater uplift to the north, where ice is largely concentrated in Alaska, up towards the ice fields in northern Alaska. And we also see that, at least regionally, uplift is largest at Camp 18 on the ice field, which I think is really interesting and definitely would have been missed in previous modeling studies. Some challenges and next steps. We have this data and some things to think about. Tectonic uplift over this time period. Seth mentioned this yesterday. This is likely not a huge component. This is in a strike slip regime of the sort of tectonic setting of Alaska. So hoping this doesn't have a major effect on our data, but there were a few earthquakes in the last few decades that are worth considering. There's seasonal loading every year. Southeast Alaska goes up and down a lot, like a centimeter, just because of the snow that falls and hydrologic cycle. There also is residual uplift from the Little Ice Age and collapse of former ice sheets. So there's some ongoing uplift from that. We have a few ideas for how we could make this better in the future. Some long-term measurements would be great. And I've heard recently about potentially some permanent GPS installations, which would like dramatically improve the resolution that we get in sort of the modern uplift rate. Okay. So that's constraining the rates. Now I'm going to move on to even more sort of preliminary ongoing work, leveraging an amazing open data set that JERP has of on ice GPS elevation since the 90s. And apologies, these figures are going to be a little rough. This is very, very fresh. On the right, in the blue dots are everywhere that JERP has taken a on ice survey point. On the left, you have a histogram of all of those data over time, and a couple time series on the bottom. So this is really nice coverage for the southern ice field for how ice is moving. I'll say that glacier's surface is moving up and down. The challenge here is that the data is unevenly distributed in both space and time. So it's not exactly obvious how we might pull out like a complete picture of ice thinning, but that's what we need in a GIA model. Still, it's really useful because the sort of the alternative is satellite observations for ice sheet thinning, which are really great, especially for the ablation zone. They can provide a complete picture of ice thinning. But on the accumulation zone, they're really noisy and uncertain. This is just an example. You can see like a really coherent signal down on the Gilkey and a really noisy, really high uncertainty signal up on the ice field. So the GPS data set provides possibly something better. I'm not going to stand up here and talk about Bayesian statistics, so I'm going to give a very high level overview. Yeah, everyone's very thankful for that, I'm sure. But basically, Bayesian approaches or data assimilation provide a really nice way to take unevenly or sparsely distributed data and infer a complete spatiotemporal field of ice change, of surface change in this case. So very simply, we take all that data, use Gaussian process regression with some Bayesian inference, which helps quantify those uncertainties really nicely, and infer something that looks like this, a spatially complete field. Here's very preliminary results. Again, sorry for the sort of weird figure, but this is an animation of the cumulative change in elevation since 1994 on the ice field based on that GPS data. And this is just sort of the net elevation change 1994 to 2018. We see this really strong gradient in surface height change from the maritime to continental sides. I'm not going to get into why. I'm sure a lot of people have thoughts about that in this room. I'm sure Daniel Otto has a lot of thoughts about this. But it's something I'm still thinking about. Also, interestingly, this greater surface lowering to the north seems to align with the greater uplift shown in that really dark red dot at Camp 18. This is super speculative, but is intriguing, and I think is suggestive that this uplift data is real and is linked to spatial gradients in ice mass change on the ice field. This approach provides uncertainty quantification. So the data is concentrated in the southern accumulation zone. So obviously all the other regions are unconstrained. We don't have data there. So that's kind of intentional. But the ultimate goal is to hopefully combine this with satellite products. So using sort of the best of both worlds in a data assimilation approach. We can get pointwise inference. So at any location, you can take a time series. You can see at this location, the yellow dots don't provide a whole story, but because we're regressing through the entire data set, we're still pulling out nuances in what the ice is doing. And then I'll just highlight for this last time period, last few years, this data hasn't been collected or is not as available online, and so these uncertainties go up. But I think it's an important period to look at because we can see this acceleration fitting right at the sort of 2010s. This is just that map view. So this is the one standard deviation of ice change from 2015 to 2025. There's no data in 2025, so it's like a totally unconstrained problem, but we can get back out there and get more of this data, we can hopefully bring this uncertainty way down. So some next steps, thinking about this gradient change from Juneau to Atlin, what's driving that continental versus maritime response to the ice sheet or the ice field. Also looking to integrate satellite data for the ablation zone with this in-situ GPS data from the accumulation zone to create a full picture of ice thinning. That's something we can actually put in a GIA model and finally relate to our uplift rates. Yeah, and this is just ongoing work, so I'm excited to hear what people think of it. And finally, just a huge, massive thank you to everyone at JERP who makes science like this possible, especially for early career researchers like me. I don't have another avenue to get out in the field and do this, so this is a really unique opportunity. Very grateful. And with that, I'll take questions. Thanks.
Great talk. Thanks, Sam. Yeah, so Scott led the GPS point surveys from I don't know what year, looking about like 1988 was when we first started doing it, until 2018, and there was just no money to cover the cost to bounce around. And I guess one thing I'm curious about, like as we advance technique, I think about when he first started doing it, it was like almost the Autolite methodology, right? And, progressed to GPS technology. And now we're in a state where it'd be nice to progress that technology a step further to still be gathering that elevation information across the ice field. We're driving snow machines all over the ice field all season long. Can we use, GPS instruments mounted on our snow machines to actually capture elevation as we're cruising along, to actually capture elevation, but also maybe capture even surface elevation change through the season, to capture melt rate. So things like that are things that I'm kind of toying with in my brain that would contribute to something like this that you're keen on, but also other projects as well. So do you have any thoughts on other things we might be able to do to kind of leverage our current efforts that bounce all over the ice field?
Yeah, I thought about this a little bit. I'm not a geodesist, but I thought about just strapping a GPS to a snowmobile and letting it run while people just are doing whatever their normal activities. And I think that can be possible to think about the uncertainties that might be introduced through that. We've mentioned sending robots out around that field. That'd be great. I don't know how near field that is. I'm getting that out there. But it does seem like something, especially with this GPS that doesn't require a base station. When people go out, if they can just take this along with them even and just throw down a few points. And it does not need to be near where Scott got his original measurements at all. It can be literally anywhere in the ice field. We can regress through that. So it's nice to hear that you're thinking about that. We should, keep chatting about it.
The most recent pitch that Scott put together is to install these two GPS and seismic kind of portable stations with Earth scope on the ice field. And a big part of that was trying to have better ground control for any GPS survey, any work that requires precision GPS survey, to have a shorter baseline and have a long-term operating network of GPS units on the ice to kind of help us with that process too. So help in the long run.
Yeah,
Type of work here.
definitely. It's really helpful.
Sam, what the background isostatic uplift rates are from the last glacial period?
Yeah, I think in this region, from the collapse of the Cordilleran ice sheet and Laurentide, it's thought to be negligible, and previous studies have just completely ignored it because your mantle viscosities are so high. So it sort of accounted for that, accommodated that. But the little ice age is a huge uncertainty in this region. And that loading and unloading definitely needs to be accounted for. And you look at the models people have for that, and it's very, very rough, approximate modeling. And there's a lot of advances we could make, like in Greenland, people have tackled this problem extensively that could be applied to Alaska. Also, I think the best LIA reconstruction that I'm aware of in Alaska is Beth Ann Davies reconstruction. So leveraging that somehow for the Juneau ice field would be great. But yeah, that background rate is probably like half of the total signal or something.
Are there like off ice stations around the margins of the ice field that show the uplift rates and how those might compare? Cause that's pretty high, 2.7.
Yeah, yeah.
A year.
So there were those two I showed, they're like 2.1, 2.6 or something. And those are the closest that I've found.
Where are those?
One's in Juneau, and the others. This one out here, I don't know how it got there. Yeah, it's on some island out there.
So they're all very similar.
Yeah. The 2.1, that's kind of like the rate that I would say like the last study generally predicted for this area.
Yeah. Do you expect it to be higher? In the margins versus the interior? For ice is already been removed completely, or?
I would expect it to be highest in the interior. Just because like everything is a pretty long wavelength signal, and then just in the middle you have the most mass loss. Unless you're really, yeah. So I would expect it in the middle. The caveat being just like there are way bigger ice fields to the north that are also melting. So if that signal is dominating this, then I would expect like an overall gradient to the north, if that makes sense. I feel like kind of what we see here, like those northern stations that are a little bit higher up.
So do you recall the uplift rates for like more central Alaska where you have more of the, that block impinging on the St. Elias and
This is model output, but they have it like 2.5 towards 3 up there at the maximum. This also, importantly, this is up till paper came out 2019, but the data is from up till 2012. So it's definitely underestimating what the modern would be, I think. So yeah, this is comparable to Greenland in a lot of places.
essentially like I was kind of expecting it to be higher because you have the mass loss and the uplift from the impinging tectonics.
Yes.
Whereas we're like the ice field is really more in that stroke slope zone.
Yeah, so and what I'm showing there on the right, that's just GIA model output, so.
Okay.
And then, yeah, that figure on the left doesn't go all the way up that high, unfortunately, but I agree, it probably would be higher, that uplift.
The combination.
Yeah.
That comes in.
Dan, I have a question. Given your vertical error, and those uplift rates, how many years do you have to wait until you can like send a whole awesome pack of Jerpers back out across the ice field and get uplift rates at all of your new base stations?
That's a great question, and I guess it depends on how good you want that that final answer to be a little bit. Like realistically, like 6 to 7 years if the methods don't improve, is what I remember calculating back on the ice field this summer. But I think now, especially that I'm confused on ice field, but now we know that like really the only two places, the best two places to do this are Camp 10 and Camp 18. If we can just leave the same gets out there for like 24, 48 hours, we can get those uncertainties down to like sub-centimeter vertical. In which case, I think 3 years to get a signal. So it would have big uncertainties, but
These portable stations where they're kind of capturing an annual signal at this point, right?
sorry.
A lot of these portable stations that Earthscope has installed, aren't they capturing signals within a year? They're installed.
Yes, depending on where they are. I think that getting it over 1 year is tricky in Alaska just because of the snow back every year.
Sorry about this, did you look at any of the relative sea level studies in the area to see how the rates of them compared to?
Speak with me. Other rates can vary. I have looked at some of the studies. There's not a lot from right around Juneau. These rates definitely exceed the Holocene, any sort of Holocene rates. But how do they compare to like LGM to present? I'm not sure.
I'd just be curious if there was any big melting previous to this. And then ever expanded, or it's been just constantly melting for the last few hundred years at least.
Oh, like between the little ice age?
Now, yeah, and movies and stuff.
Yeah, I'm not sure. That is definitely a tricky period, like we just don't, really know too well.
Thanks, Sam.
Thanks.